Hello and welcome to today's webinar. Today we're going to discuss the use of Fronius string inverters in commercial systems. I would like to introduce your Fronius team for today. I'm Mohammed Sidat. I'm the Technical Sales Advisor for Fronius South Africa. So I take care of the Southern African market for Fronius. I'd like to also introduce my colleague, Cyprian, who is the Technical Sales Advisor. And he's responsible for the entire English-speaking Western African region. And he operates from Fronius International. I would also like to introduce my colleague David, who is a Technical Sales Advisor for Eastern Africa. And he also operates from Fronius International. Just to give you more information on the regions that we are each responsible for. So my colleague David, he's responsible for all the countries that are indicated as red in the picture. And that's the majority of the Eastern African countries, as well as certain, Central African countries, and also certain Southern African countries. Then my colleague Cyprian, he's in charge of those countries in the blue. That's primarily English-speaking Western African countries. So if you reside in one of those countries and you'd like to find further information, Cyprian is your person to contact. Then myself, I'm responsible for the Southern African region. So all those countries in green. So if you do reside in one of those countries and you are an installer, you are more than welcome to contact me for your upcoming Fronius projects. I'd also like to show you our different distributors in the markets. So as I showed you in the previous slide, we have 3 permanent employees in Fronius Sub-Sahara for the Sub-Saharan region. However, on top of that, we also have distributors in the Sub-Saharan African region. So for example, these are all our distributors currently in the Sub-Saharan region. And if you, for example, an installer in South Africa, your distributor will either be Innomatic Solar or IBC Solar. If, for example, you are in Namibia, your distributor will be Radio Electron. If you are in Zimbabwe, your distributor will be One Stop Solar. If, for example, you are in Ghana, your distributor will be Tino Solutions. If you are in Kenya, your distributor could either be CAT, GreenSpark, or CAT or GreenSpark or Knights Energy. If you are, for example, in Nigeria, Components and Solutions will be your distributor. If you are in Senegal, it will be Sonikara. Then if you are in Madagascar, it will be Mother Green Power. So all our distributors stock Fronius inverters that are ready to be sold. However, they also stock replacement parts. So you can really see the advantage when using a Fronius inverter for projects is that all our replacement parts are stocked locally in Sub-Saharan Africa. So that's really great. So it means that if you have an issue with the Fronius inverter, we can get you a replacement part within a few days. Okay. Our distributors also provide the first line of support. So if you do have an issue, the first point of contact is the distributor. Okay, so our distributors have trained technicians that are willing to drive to site, assist clients, and also willing to take your calls to assist and provide you support. Okay, moving on to today's agenda, we're going to discuss the Fronius inverter solutions. We're then going to have a look at the Snap inverter series. After which, my colleagues will then take you through the project planning with Snap inverters. We'll have a look at the solar configurator. We'll then have a look at the project planning with the Tyro inverter. We'll then also have a look at the Tyro configurator, after which we'll have a look at system analysis and maintenance. And we'll then end today's webinar with some further information. We shall now start off with the current Fronius inverter solutions. So currently from Fronius, we have been producing inverters since 1995. Our first real commercial inverter, so to speak, was the Fronius Agilo. This is a big central inverter. In 2013, we then introduced our new range of inverters. So for example, if you look at on the commercial range, it would be the Cyma and the Eco. Then at the end of last year and the beginning of this year, we started introducing the Gen 24 Plus. And this year, we will also be introducing the Fronius Tyro, which is our big commercial inverter. So currently on the market, Fronius will eventually have these 4 inverters. Okay, so currently what you can buy is the Fronius Eco and the Fronius Simo. In about 2 or 3 months' time, you will be able to buy the Taro and the Taro Eco. Okay, so beginning with the Fronius Eco, that comes as a 25 or 27 kilowatt variant, and your MPPT tracking voltage range is between 580 to 850 volts. So whenever you're planning your strings, please make sure that your voltage per string is somewhere within this range to ensure the optimal performance from your inverter. Then moving on to the Fronius Simo, it comes in power classes of between 10 to 20 kilowatts. Your MPPT voltage range is between 200 and 800 volts DC. So again, please try and get your strings within this voltage range. You can see that the Simo has a much higher range than the Eco in terms of the MPPT voltage range, and this is because the Simo has a booster circuit integrated in the inverter, whereas the Eco does not have that booster circuit. Then moving on, we're also going to have a look at the Fronius Taro. This is a 50 kilowatt inverter, and your MPPT voltage range is between 400 to 870 volts. Then looking at the Taro Eco, this inverter will either come as a 50 or 100 kilowatt variant, and your MPPT voltage range will be between 580 and 930 volts DC. Okay, remember, all of these inverters can have a maximum of 1000 volts DC per string. We'll now look into more detail on the Snap inverter series on the commercial range. So for the commercial range, we have 2 inverters on the Snap inverter series, that being the Fronius Simo. As I said earlier on, it comes in these power classes. It has 2 trackers, and you can have 3 strings per tracker of 1000 volts DC each. It's a Superflex design, which basically means that you can unbalance your trackers. Then having a look at the Fronius Eco, it comes either as a 25 or 27 kilowatt variant. However, in Sub-Saharan Africa, you're most likely only going to get the 27 kilowatt variant. Okay, this is optimized for commercial systems, and it has 1 tracker, which you can connect up to 6 strings to the inverter. So where would the Snap inverters be used? They would really be used in systems that are between 50 kilowatts and 1 megawatt in size. Okay, so for example, these would typically be supermarkets, commercial buildings, company buildings, warehouses, farms, etc. You can also combine an Eco and a Simo together. That's also possible. And the features with our Eco and the Simo is that we have a high flexibility in design. You don't need any additional components. So you don't need DC combiners. You don't need additional external SPDs on the DC side. Also, what's to note is that one master inverter with a data manager can control multiple inverters. So for example, in this picture over here, we have 4 inverters, but only one of them has a data manager. Okay, so the other 3 inverters receive all the instructions from the master. With this sort of topology, it's a very cost-optimized solution. So you can really save costs on, DC cabling, AC cabling, combiner boxes, surge protection, etc. Our Snap inverters come with what is called the Snap inverter concept. Okay, so that's really where the name comes from. So Snap stands for the method in which the inverter is installed onto the backplates. As you can see, your front of the inverter, where all your power electronics is basically snapped onto the backplates. Okay. You can also see that all your AC and DC connections are integrated on the backplates. Okay. So this will really allow for fast and quick installation as well as service. Our Snap inverters all come with what we call active cooling. So with active cooling, for example, we have a Fronius Simo, which has 2 fans. Okay, so 1 fan on the left-hand side, 1 fan on the right-hand side. And it then takes cool air from the environment and passes this air over the heatsink. Okay, so your heatsink is located over here, and the hot air then escapes from the top of the inverter. Okay, so this is very important when it comes to mounting multiple Fronius inverters. So you do need to leave a little gap between each Fronius inverter, and that's because of the fans on the sides of the inverter. Okay, this is just a closer image of how the heatsink actually looks like. So here we can clearly see the air being pulled in and then passed over the heatsink, and then it will then escape from the top of the inverter. Using active cooling, we can really achieve mounting locations from minus 25 degrees Celsius up to 60 degrees Celsius ambient temperature. And the protection class is IP65. So in this picture over here, we can see that this inverter is under operation. At the same time, they're spraying water at the inverter in all directions. Okay, so this means the inverter can be installed indoors or outdoors. It is waterproof and dustproof according to these IP65 ratings. I'm just going to show you a temperature derating curve of a Fronius Cyborg 20 kilowatts inverter. Here you can clearly see on the x-axis we have your ambient temperature, on the y-axis we have your output power. We're then comparing 3 voltage levels coming from your strings. So we're comparing 420 volts DC with 600 volts DC and with 800 volts DC. You can clearly see the lower the DC is coming from the panels, the quicker any inverter will start to derate, okay, including the Fronius Cyborg. So the Fronius Cyborg 20 kilowatt unit will start to derate when operating at 420 volts DC at about 45 degrees Celsius ambient temperature. However, the higher the voltage is, so for example, if you're looking at 800 volts DC, we'll only start to derate after about 55 degrees Celsius. If you look at the internal temperature of a Fronius inverter, it will usually be plus minus 20 degrees higher than what the ambient temperature is. So for example, if the temperature at the heatsink is 80 degrees Celsius, it kind of implies that the ambient temperature is around 50 or 60 degrees Celsius, okay? And this will, in turn, cause the inverter to shut down because then it's overheating. So if the inverter's internal temperature does go above 80 degrees Celsius, it will give you error 304. Okay, and that means that you clearly have an issue with either the fan or maybe there's been an installation error. Moving on to the Superflex design, only the Fronius Cyborg will have the Superflex design from the commercial snap inverters. And basically what the Superflex design implies is that you can start from 150 volts DC up to 1000 volts DC per string, okay? Your dimensioning can be 6 to 24 modules. You can also have an odd number of modules. Your over dimensioning can also go up to 150%. And also comes with 2 MPPT trackers. What you can also do is that you can unbalance your trackers. So you can, for example, add 80% on tracker 1 and then add 20% on tracker 2, and you will not get any system, unperformance or deperformance. You can also have a symmetric distribution. So you can also, balance your trackers. That's completely fine. Moving on, I'd also like to discuss the dynamic peak manager. So both the Eco and the Cyborg comes with the integrated dynamic peak manager. And basically what that is, it's an MPPT tracking algorithm that always ensures that you get maximum yield. Okay, so it always locates the best operating power points, even with shading. Okay, so here we have an example of a chimney on a rooftop, and this chimney throughout the day produces a shadow that changes and produces a 360-degree, depending on which hour of the day it will affect certain panels. So in this case, we can see that it's affecting about 3 panels, 2 or 3 panels really bad, and then it's affecting the other panels next to it as well. Because remember, as soon as we have shading on one panel, all the panels in that string will be affected. Okay, because remember, if a panel is shaded, the current automatically decreases, which in turn will also affect the other panels in the string. So with our MPPT tracking algorithm, we try to ensure that we can try and overcompensate for the shading in order to provide you a better operating power point. Okay, so these curves really explain it well. So I have a blue curve, and this blue curve is when we have no shading. Okay, and the red curve is when we have partial shading. So if you install an inverter without an optimizer, you'll get the local maximum power points. However, if you install an inverter with the optimizer, for example, a Fronius, we will always give you the global maximum power point. And here we can see the improvement from local to global of about 20 to 30%. Then looking at the black curve we can see is complete shading. So with complete shading, if you install an inverter without an optimizer, it will give you the local maximum power points. However, if you install an inverter such as Fronius with an optimizer, it will give you the global maximum power points. And I'd also just like to add, whenever you purchase a Fronius inverter, you're already purchasing the integrated optimizer with it. So there's no additional need to purchase external optimizers, which in turn will lead to more installation time for the installer. And as you all know, if you have 20 or 30 optimizers sitting on the roof, in a few years' time, you're going to have to go back to your client to service those optimizers. Okay, so my tip is always try not to have optimizers in your roof, because in turn that's going to lead to more issues for the installer. Okay, moving on to the different options that can be ordered with the Eco and the SIMO. Starting with the overvoltage protection, you can order SPD type 1+2 or type 2 on the DC side, and this is applicable for the SIMO and the Eco. Okay, you can also choose to order a DC connector kit. Okay, so this is applicable for both inverters as well. And we get 2 DC connector kits. We get one for a 25mm squared cable and one for a 35mm squared cable. Okay, the only reason you're going to be using a DC connector kit is that if you are using a DC combiner box. Because remember, if you're using a DC combiner box, your cables are going to be quite thick. And in turn, your cables could be about 20mm squared thick or even 35mm squared thick. In that reason, you'll have to use the DC connector kit. Okay, moving on. Our inverters can also be ordered with string fuses. So only the Eco can be ordered with string fuses, so not the SIMO. If you are buying the Eco, you can order it with 15 amp string fuses. And this is internally integrated in the inverter itself. Okay, moving on, use of snap inverters for commercial systems. So when it comes to really big commercial systems, and as I showed you earlier on, if it's less than 1 megawatt, a good suggestion is always look at the Fronius Eco. The reason for that is that we have a very high system voltage on the Eco, so we can do 1000 volts DC per string. And our MPPT tracking range is from 580 to 850 volts. Some of you might ask, why is 580 such a big value? Well, if you're looking at big commercial systems, you're most likely going to have long strings. So in order to get 580 volts on long strings, it's quite easy on a big commercial system. You also get a very high grade of efficiency, and the reason for this is that we don't have a DC booster. Okay. With the Fronius Eco, you can directly connect 6 strings of 1000 volts DC directly to the inverter. So again, there's no real need for any DC conjunction boxes. Okay. You can also get the overvoltage protection on the DC side, as I showed you earlier on. Your fuses are also integrated. You have a really low weight, which is 36 kilograms. And with such a low weight, it actually means that you can actually pole mount this inverter. So you can technically mount this inverter directly underneath your panels. And this again will ensure that you have lower DC cabling costs. We are considered to have the highest power density within our class. And as I said earlier on, we are IP66. So you can install the Eco indoors or outdoors. Then looking at the Fronius SIMO, what are the advantages of the SIMO? So it's 1000 volts DC max per string. Your MPPT voltage range is much wider than the Eco. Okay, so from 200 volts to 800 volts DC. And with the SIMO, you can sort of do shorter strings than with the Eco. With the SIMO, we have Superflex Design. And with the Superflex Design, we have a DC booster. And this is why our range is much better than the Eco. Okay. With the SIMO, we have 2 trackers, and you can have 3 strings on each tracker. And the good thing about 2 trackers, if your PV installation is facing 2 different directions, you can put the one direction on tracker 1 and the other direction on tracker 2. Okay. With the SIMO, we also have your overvoltage protection on the DC side. That is optional, as I showed you earlier on. It does not have fuse holders, so just take note of that. It is a lowered weight, so with the SIMO, it's 43.4 kilograms. And with the SIMO, it's a really compact construction. So we basically have also one of the highest power densities within our class. Protection class is IP66 as well for these SIMO. Okay, now having a look at decentral versus central topologies, you can really choose with a snap inverter whether you want to go for a decentral or a central topology. Okay, so in the first case, we have a central topology. This is where your snap inverter is located as close as possible to the AC side. Okay, so here we have really short AC cables, but then we have really long DC cables. Okay, if you are going to do it this way, the suggestion is that you do you don't use the additional connecting. Then moving on to the second decentral topology, this allows direct connection of the strings to the inverter. Okay, so here we have really short DC strings. Okay, but then we have a really long AC cable. Okay, going to our local transformer. So you then have to decide as an installer, does it make more sense to use a central or decentral topology based on your various calculations. Okay, so I'm basically showing you a picture of Fronius inverters that are stringed to each other, which are then in turn connected to an AC combiner box. and then the power from this AC combiner box is then sent to a local transformer. On the right-hand side, I'm basically showing you what happens when we use the DC connector kit from Fronius. Okay, so you only use the DC connector kit from Fronius if you are using a DC combiner box. So if you're using a DC combiner box, you need to use this DC connection kit from Fronius. And as you can see how they actually plug into the DC plus points and DC minus points. Okay, so this is how the DC disconnectors actually look physically installed in a Fronius inverter. I would now like to hand over to my colleague, Cyprian, who will take you through the second half of the presentation. Cyprian?
Yeah, thanks a lot, Mo, for your wonderful presentation. I will be continuing from this point, and I believe you can all see my screen now. So I will be continuing with system design with Fronius Solar Configurator, and then subsequently continue with the Taro Configurator, which is a new online configuration platform. So starting with the Fronius Solar Configurator. Let me pick my pointer. Yes, so first off, I would like to know that it's an online tool for those that don't know that can be used to design individual customer projects. It's free of charge and then easily usable and of course user friendly. Yeah, this is how it looks like. For want of time, I will just straight up give you a bit of a demonstration how it looks like, and then give you all the necessary explanations I was supposed to do on this particular slide. So without further ado, let's see. Yeah, so to make it straightforward, I decided that we'll do it together. So first off, I think you can do is copy this link on the slide and paste it on your web browser. Okay. So once that is done, it's going to take you straight up to the Solar Configurator platform, where you can now conveniently do your system configuration, as we can now see. So it's basically divided into three parts: the PV module part, the inverter part, and the general part. So for the PV module part, that's where you make your PV module selection, and then the inverter selection comes in on the inverter section, and then you now do your general settings on this general part. So for the PV module, you can basically select any PV module that you intend to use for your project. We always update the PV module manufacturer and of course the modules that they produce. So if you want to say go for the popular modules, say Canadian Solar or Jinko, for example, if you type, of course the name will pop up, and once you click on it, it will now populate all the available modules. And then you can now make your selection of whatever module you want to use. Say, let's pick this one, for example. And then once we select that, you can have the data of this particular module that you have selected, as we can see, ranging from the open circuit voltage to temperature coefficients, as you can all see, and of course, dimensions too. So once that is done, you get all the information you need about the module. You can now proceed to the inverter section, where you can select your country, select this inverter series, and then select the particular inverter you want to use. So since we're dealing with a project or a large commercial inverter, we would now go for the Echo. Yeah, they will have it say Echo 25 or Echo 27, as you please, which is the highest capacity in the Echo family. And then, of course, remember to select your module temperature depending on the ambient temperature of the site. Here, by default, it's -10 to 70 degrees centigrade. That is 14 degrees to 158 degrees Fahrenheit. One thing I would like you to know here is that, of course, you would have an idea of the annual power consumption for the particular site, and then your information, if it's the information on the load profile, if it's employed or family. For employed, it basically means that it's a setup that uses most of the power at night. That's the simple explanation. Then for family, it simply means this is a setup that uses the power during the daytime. More power during the daytime, that is. Yeah. So as you can see, with our selection, it has already populated the possible combinations that are available. So because this is just a quick example, you can feel free to go through the link and then play around with it and see how you can best adapt it to your project. So for this case, for this particular inverter, the Eco 27, you can have as much as 96 modules connected, and of course you can do this by connecting 24 modules per string. You can have as much as 4 strings. That is an option. The other option is you can connect as much as 120 modules, as you can see in this case. So you would have 5 strings with 24 modules connected per string. So if you click on it, you're going to have a summary of this detail, this string detail. And with this, like I said, this is for a particular echo, just one echo. So with this, you have an information on how to extrapolate and go bigger in terms of the capacity up to the capacity you are designing for. So let's go back to the presentation. Due apologies if this was too short, but it's because of limited time. So, but feel free, use the link and then just play around with it. If you have any inquiries, of course, you can reach any one of us, depending according to your region. So, continuing with this, I'm just going to give you a few references. So these are with what I've showed you. Large installation, of course, are possible, like this example in the Philippines. Because of regulations regarding zero feeding, this 4.7 megawatts roof-mounted system is basically used for self-consumption. And as you can see here, all the inverters stationed and installed and then feeding off from this array of PV modules. Another example is the largest installation in Ukraine, which is approximately 52 megawatts. The size, yes, approximately 52 megawatts. It's a field installation in this case. The other one was a rooftop installation. You can see the detail of the module type, the inverters. And as my colleague, Mohammed Sidat, mentioned earlier, all the inverters mustn't have web servers, as in they mustn't have data managers. So here in this case, you can see that 65 of the inverters had data managers, and then the other ones were light versions. So meaning that the communication were appropriated amongst these 65 Fronius Eco 27 inverters. So in total 1,923 inverters were used in this case, and to generate an annual yield of 67 megawatt hour. And this has been commissioned since October 2018. So you can also see how the subsystem is actually built from this exact picture you can see here. So going forward, we're now going to take a look at how to make use of the Taro for commercial systems. As we all know, the Taro is a new series of new series of inverters dedicated for large commercial purposes, ranging between 50 to 100 kilowatts, as Mohammed has rightly stated earlier. We have 2 versions of this Echo for the Taro Echo. We have the Taro Echo D and Taro Echo P. So for D simply stands for direct, while P stands for pre-combined. So yeah, so with the direct connections, it means that your inverters installed pretty close to the modules, so you can have your MC connection plugs and then have up to from 14 to 22 strings connected, and then have a long run of AC connection to the AC distribution panel. And then, of course, for the pre-combined version, you can have up to 3 times 90 mm squared cables and with V-clamps. I'll tell you more about this V-clamp because it's a special feature in the Taro inverter. So in this case, you have to use a DC junction box or DC combiner box, and then have a long run of a thick DC cable. So for the decentralized topology, which is also called the D version or the D variant, all the inverters in the system are placed near the PV modules, as earlier stated. In this case, we'll have to go with a long run of AC cable, and then additional AC combiners and different cable diameters might be necessary in this case during the combination. Yeah, in terms of our cost advantage, we're looking at the balance of cost, that's BOS. No additional DC components are necessary in this case, so you don't need a DC combiner box or fusing. And then for power advantage, of course, you have low DC cable losses because you're using shorter runs of DC cable. And then additional advantage includes flexibility in terms of DC string fuses inside inverter, which is already available inside inverter, reduce installation effort because you would not be using DC combiner boxes, and of course, availability of string monitoring. So for the centralized version, which is also called P or the pre-combined version, the inverters of this system are placed near the feeding point. In this case, you would have to go with longer run of DC cable, and then of course have to make use of DC combiner boxes. So in terms of BOS cost advantage, no DC connection kit is necessary because of the availability of V clamps. Like I said, I would say a bit more about this in subsequent slides. In terms of power advantage, you tend to have low DC losses. This is because of the cross-sectional area of the DC cables you will be using, you can use. Because of the larger the cross-sectional area, of course, it implies or is inversely proportional to the losses, the electrical losses you will incur. So further advantages include that you have the ability or the possibility of connecting up to 3 times 90 mm squared DC cable because of the inlets provided in the inverters. We're going to see that also in subsequent slides. And then, of course, easy installation because of the big clamps. And then, of course, longer cabling is possible in this case. So let's go to the next slide where I now show you what the V-clamp looks like. So for AC connection, you can go as high as 240 mm squared, which is quite great. For the inverter, it has V-clamps and makes it very, very easy for cable connection. V-clamp, of course, eliminates the use of cable lugs. So you don't need any cable lug. All you need to do is to strip the cable and connect it directly. So this, as I'm showing you here, is the positioning where the V-clamps are available for connection. And as you can see here, this is how it looks isometrically. And then taking a closer look at it, it can actually span, you can actually connect cables of cross-sectional area from 35 mm squared to 240 mm squared. As you can see, this part up here can actually be inverted. So for smaller cable diameters, it's connected this way, and then for larger cable diameters, it can be inverted and connected as we can see. So in this case, the cost advantage is that there's no necessity for using cable lugs anymore. And then, of course, aluminum and copper can be used. Aluminum and copper cable can be used. And of course, no special power tools is necessary because of the ease of connection. It can cause low cable losses. And then other advantages include that the cable diameter can freely be tuned to optimize BOS costs, as already explained. So let's come to AC daisy chaining, which is another special feature in the Taro inverter. You can actually AC daisy chain inverters together and go out with a common outlet per se. So you can go as high as 200 kilowatts, meaning that you can have 2 AC daisy chained 100 kilowatts Taro Echo or 4 AC daisy chained 50 kilowatts Taro Echo, as we can see. And I'm going to show you how advantageous this can be in the coming slides. In terms of cost advantage, no AC combiner is necessary, and you can connect up to 200 kilowatts, as earlier stated. And then, of course, you tend to incur low AC losses, and then, of course, reduce installation effort and high design flexibility. So, like I said, giving you a good example of how this comes into play in terms of BOS costs, cost reduction using the AC daisy chaining. Normally, this is how it would look like, because if you have subsystems, you now have to combine the AC outputs and then recombine them again in order to connect to the grid. But with the AC daisy chaining, it eliminates all stress by simply connecting or AC daisy chaining all the inverters and then going out with just one run of cable to the main AC distribution panel. So Taro options include AC daisy chaining, which comes with double V clamps. Of course, you have the option to include a DC surge protection device on the DC side, of course. And then, of course, it can also come with an AC disconnector. So, yes, in terms of inverter efficiency, it comes with active cooling design because the temperature controlled fans and the heatsink makes it possible to avoid hotspots and, of course, increases the efficiency and, of course, extends the lifetime of the inverter. As my colleague Mohammed has earlier stated, the rating takes longer in terms of our inverters as compared to other competitors. In terms of power advantage, it comes with a lesser power derating, and of course you can have full power up to ambient temperature of 50 degrees Celsius, and of course it makes the system pretty rugged and adaptable anywhere. Further advantage includes that both horizontal and vertical installation is possible, low service costs, low weight because low weight of the heatsink, and of course less cooling channel cleaning. Yeah, so this is basically a description of how the active cooling process goes. Of course, cool air is letting, and then hot air. This, of course, creates a pressure point that ejects the hot air generated by the power electronics in the inverter. So, in terms of service concept, component exchange is possible. So Taro enables easy component exchange because even the power stage can be easily exchanged by just one single person without necessarily exchanging the whole inverter, as we can see. So if there's any issues at all, if there is, which is in most cases unlikely, you can conveniently carry out inverter servicing on site, and just one person can do this change because of the modularized nature of So, like I promised, so we're going to go through system design with the Fronius configurator. So once again, I will have to go to, so this is how it looks like, the default homepage. And like we did with the Fronius solar configurator, we will do the same with Taro. So you can copy this link and then, of course, paste it on your browser, and it will now take you to the homepage of the Taro configurator. This is, of course, a new online tool that have been developed by Fronius to help us configure our projects when using or trying to design large installations. For want of time, this is going to be a very quick one. So here you can basically start, and then it will give you an option of the system you want to implement, if it is a centralized system or a decentralized system. If you don't know what, if you need more information, you don't know what it entails, you can click this information button and it will tell you everything you need to know about a centralized system. Same with the decentralized system, as you can see. Then if you now have all the necessary information you need and have now made a decision, you can now select the system you want to configure. If it's a centralized system like I've clicked, you can now go ahead to click on or select the inverter types. As you can see, we have the Taro Echo 50, 99 and 100. Why 99? Yeah, in some countries there are restrictions in terms of the capacity you can go. Some countries have that restriction that you cannot go up to 1 megawatt, for example. So in this example, you can now have 10 units of the Taro Echo 99 to give you 990 kilowatts. So by doing so, you haven't breached any regulations. So that's why this variant is also available. So say you go for the Taro Echo 100, you can now make an option for the fuses, but in this case, Taro Echo in the T variant does not require any built-in fuses inside the inverter, but mind you that this fuse must of course be included in the DC junction box. So for SPDs, you have two variants, type 1 plus 2 and type 2, type 1. Type 1 plus 2 basically consists of lightning arrestor and overvoltage arrestor. And then type 2 only consists of the voltage arrestor only. So depending on your region and your specification, you can now make the choice of which SPD type you want to use. Then if I select what type 1 plus 2, to now take it to the next stage of the AC connection. If you want to carry out AC daisy chaining, you select this option. If you're going with the single core cables, you're going with this option. That is line 1, line 2, line 3, single core, and then your neutral and your earth, as can be seen. But if you were going with a multi-core cable, you have a bigger inlet that would accommodate all the multi-core cable and with your ground, of course. So this makes it easy for you to select and know how your system is going to look like. A point of note here is that if you select AC daisy chaining, you will not have the option of AC disconnector. And then, of course, if you now select any of these, either this single core or multi-core, you now have the possibility of AC disconnector. If you now make your choice, it will, of course, now take you to the point where you will now have to make your final assessment of the system you have selected. Select the quantity of inverter you want to use. In this case, we've selected just one, and then go ahead to send, of course, enter your product, the project name, the country, location, and the size. Select accessories if needed. If you want to install it horizontally, you would need floor mounting racks. This is how they look in case you don't know. If you need protection hoses, this is how it looks. And then if you want a disconnector locking device, this is how it also looks. And then you can now include this in your order if necessary, and then proceed to send an email to Fronius, where you can now get the quotes and, of course, continued help in the project design and execution, as you can see. So it's also possible to be exported in CSV format. So let's go back to the presentation. I hope we got good information on that. Sorry for the fast nature of the presentation, just because of time. So let's continue. So just giving you an example of such an installation. This one is in Costa Rica, Greece, where we have a mixture of 13 Taro Echo 150 spanning up to 1.2 megawatt PV system, as you can see. And then, so let's take a brief look at system analysis. So system analysis, most importantly, how efficient and how productive your system would be also depends on the cost. In fact, it's actually a major factor. And we know that when we're dealing with costs, it comes with other components. So the total cost of ownership of any particular installation comes with Capex and Opex, that is capital expenditure, and operational expenditure. And these two expenditures can actually be minimized by the use of our inverters. So to tell us more how this can be achieved, will be my colleague, David Mwangi, who will be taking over from this point. But before I do that, I would like to launch a poll question, just a quick one. Yeah, so I believe we can see the poll question now. So it says, as an installer or EPC, what is your highest installation capacity? So here you have the option 20 to 50 kilowatts, 50 to 100 kilowatts, 100 to 500 kilowatts, and 500 to 1 megawatt, and then above 1 megawatt. So please would like to have your share your answers, and so that we can have a good understanding of what your installation capacities are. I will be leaving the poll for about 5 seconds before I close it and share the results. So thank you very much for your contribution. I will now be closing. I can see some more attendees are actually still posting their answers. Okay, I will close it at this point and share the results. So as can be seen, we have a good mix of installation capacities across installers and attendees here. So we have 18 to 20% going for 50 kilowatts, 18% going for 20 to 50 kilowatts, 27% going for 50 to 100 kilowatts, none for 100 to 500 kilowatts, 18% for 500 to 1 megawatt, and then 36% above 1 megawatt, which is quite good to know. So in all these cases, we have the product, the right product for your project execution. So thank you very much. I will now hide it, and then hand over presentation rights to David. So David, you may now continue.
All right. So thank you very much, Cyprian, for your presentation. So I'll be taking over and carry through the remaining section of the webinar. So if you could give me presenter rights at this point.
Yes, it was a kind of a delay. So yes, I think I've sorted out now. So you have presenter rights.
Okay. Great. So let's now proceed and look at the economics of a commercial system, because as an installer or a system designer, there are some factors that you need to think about. Some people would like to think about short-term factors that would influence on the cost of the system, but it's also good to look at the long-term factors that have an impact on, let's say, the total cost of ownership, as already explained before by my colleague. But to start, we are going to look at the Capex analysis. So the first thing that you need to bear in mind is for you to make the best decision on the inverter to use. It's not enough to just consider the cost of the inverter alone. So you have to decide based on the comparison of all the incurred costs plus the expected yields. So for every cost you incur, there must be a projection of how much, therefore, is the system going to earn for you, for as far as a return on investment analysis is concerned. So this comparison is also very important when you're considering your capital expenditure. So in our webinar today, we are going to be comparing two inverters. One would be the Fronius Eco 27 kilowatt and a 60-watt competitor inverter. So this is one inverter with a capacity of 60 kilowatt output on the AC side. And in this example, we will be considering a roof-mounted system with a capacity of 400 kilowatt peak on the PV side installed capacity. And this system is situated in Central Europe. So this gives you an overview of how the system looks like on the roof. So as mentioned, these are the key parameters of the system. So with installed PV capacity of 408 kilowatt peak, but on the inverter side, we are having a total of 360 kVA. So in terms of inverters that are required, On the Eco side, we require 13 Eco 27s, and on the competitor with a 60 kilowatt inverter, we require 6 of those inverters. Going deeper and looking at the Capex overview, these are the initial system costs. So we can see a breakdown or a pie chart here that is breaking down the costs of the system as far as the Capex is concerned. So what you can see incidentally is the fact that, of course, the modules will form the biggest chunk of the cost as far as Capex. This is followed by the balance of system components, and then we have labor and associated costs. And then, surprisingly or not, the inverter will come in at only 9% of the entire Capex expenditure, or the initial expenditure for the system. But nonetheless, with this 9% of the inverter is going to have a big influence on the performance as well as the return on investment of the entire system. Therefore, as I've seen here, the balance of system components compared to the inverter are giving you a much higher share of the Capex at 33%. And therefore, the question that we would like to ask ourselves at this point is, how can intelligent system design influence these costs? As mentioned, are you going to think about only the short-term factors in terms of if you are trying to win the project, if you are bidding competitively with other installers as well? Or are you going to go further and analyze what is the actual impact of the system that you're going to design in terms of operating and maintaining the system is concerned? So Capex, of course, is an important factor for determining the return on investment. However, going further, we dig deeper into the balance of system components, and the balance of system components would be comprised of these key components. We have here the racking system, which is taking about 31%, and then at 41%, we have the grid connection. This is including the transformer, switchgear, and stuff like that. And of course, we also do have the DC-AC combiner boxes, which are taking about 20%. And then things like cable trays and conduiting, which are taking about 8% of the balance of system costs. So the costs are not related to the panel or the solar panels that you choose. So these have nothing to do with the cost of the inverter or the solar panels. So the racking system, cable trays, and main grid connection, these are not affected at all by the inverter. But the inverter, if you choose the right inverter for your project, can have a significant impact, especially on the AC and DC cabling, as well as the AC and DC combiner boxes or distribution boxes. So with the right system design, therefore choosing the right inverter can make huge savings in the long term. And also the model cost calculations, as I had mentioned before, we are going to analyze our Eco inverter 27 kilowatt, and also this 60 kilowatt competitor inverter. Also, as already explained by my colleagues, we are going to go into a comparison that is analyzing both a centralized and decentralized systems. So let's look at a centralized setup. And this centralized setup, we are going to start off by using or looking at a Fronius Eco setup. And we can see here from the PV side, we have a connection distance of about 45 meters to the string combiner box. So in this case, because we have all the inverters collected at one point, we are going to run, as already explained by my colleague Cyprian, from the combiner boxes on the DC side with a longer distance of DC cable to the inverter. So therefore, we have a relatively longer distance from the DC combiner box to the inverter. And this is covering about 80 meters. So, and then from the inverter to the AC combiner boxes, we are covering that with 10 meters. And then from the combiner boxes on the AC side to the feeding point, we are going there with about 10 meters of cabling. And the size of the cables that will be required also indicated here. From the PV side, 6 millimeter square. From the DC combiner boxes to the inverter, we are going there with 35 millimeter square. And then from the inverter to the AC combiner boxes with 16 millimeter square. And then once you have combined all the AC outputs from the inverter, then going to the transformer or the point of interaction, we are going there with much thicker cables at 70 millimeter square. So putting all this cost together on the DC side, this particular example was costing about 4,301 euros plus 1560. Then when we add the cost elements on the AC side, which is 447 plus 1,445, and the total cost as far as the balance of system components are concerned for this particular project example were 7,753 euros. So what we can note here, of course, as mentioned, is that the strings are collected in a string combiner box, and only 2 combiner box cables, therefore, are running from the combiner boxes to the echo inverter. The DC cabling then from the panels to each inverter is much longer than the AC cable from the inverter to the AC distributor, as already mentioned, to differentiate between centralized and decentralized. Having looked at the echo, let's now look at the 60 kilowatt inverter, what that would mean if you are to use a bigger inverter from a competitor. Nearly the same distances with just very slight variations. As you can see here, I would also like to mention here that with the Fronius Echo inverter, we do require about 13 string combiner boxes, but with the with a larger inverter, we are going to need only 6 string combiner boxes. Therefore, we can see also there is a change of the costing because the current handling capacity of the combiner boxes is slightly different. So the current required for the Fronius section is slightly less than on the 60 kilowatt competitor, and therefore these combiner boxes are slightly more expensive. And then same distance for the DC from the combiner box to the inverter. So looking at the total summation of the DC and AC side with the 60 kilowatt inverter, we are looking at 9,816 euros. So the key difference here in cost would be due to mainly the cable cross sections that are used. Also, if you look at the combiner boxes and the distribution as far as the AC side is concerned, these are also having an effect on the actual cost of the balance of system component as far as cabling is concerned. And therefore, if you compute the difference between the 2 designs, one that is using a Fronius Echo and another one that is using a 60 kilowatt competitor, we see that we are in favor of a Fronius Echo by a factor of about 2,063 euros in favor of the Fronius Echo. So I just like to mention quickly here that we do seem that we are going to run slightly over time. So kindly bear with us and you're going to be able to cover the remaining section of the presentation. So we are going to do our best in the next 10 minutes to go through all the content. So now looking at the decentralized systems, the Fronius Echo would of course require on the DC side, from the panels to the inverter, the string are now connected directly to the inverter, and therefore we are going to use only 6 millimeter cables, as also a slightly short distance from the inverter to the AC combiner. But then from the AC combiner to the feeding point or the transformer, we are going there with a much longer distance of cable, and therefore we are going to need a thickness of about 240 millimeter square as far as the AC cable is concerned. So as already differentiated, we are covering a longer distance with the AC cables compared to the DC cable, and therefore bigger sections as far as cross sections on the AC side will be required. So the total for the 2 sections will be 6,923 euros. And then looking at the competitor, just nearly the same factors, we are going to come to a cost of 10,327 euros for the 60 kilowatt competitor. And then if you look at closely what are the key cost drivers in this case, you find that because of the thicker cable cross sections as well as the AC combiner boxes that we do require, other balance of system components as a result of the design therefore have a significant effect on the cost. We are talking about surge arresters, AC fuses that may be required. As already mentioned, the Fronius inverters integrate the SPDs, therefore you can save a bit of costing there as well, if you're especially looking at the Tauro. And therefore, the difference between a decentralized system using a Fronius Echo 27 inverter arrangement and 60 kilowatt competitor would give you about 3,400 euros as far as BOS costs are concerned in favor of Fronius Echo. So this therefore gives us a summary of how these costs arrived at, and we can see therefore in general we have about 62% difference between the lowest cost indication using a Fronius Echo and the highest cost indication using the competitor inverter at 60 kilowatts. And therefore, it becomes very apparent that even though some inverters might seem to be slightly less expensive in the beginning, but in the long term, once you put in the cost of balance of system component, and then you analyze what is the total cost of ownership of this system, you find that a Fronius inverter will give you a lot more advantages in this regard. So what therefore influences the BOS costs? As a summary, therefore, we can talk about what is the distance from the PV module to the point of interaction, or the feeding point in this case. That has to be a big consideration for you when you're designing the system. And then of course, we have to look at the cable cross sections that are used. What is the system design? What is optimal for you? Are you going to go as a system designer for a centralized system or a decentralized system? So in the beginning, when you are going to bid for a project, I think it's always very important to look at all these cost elements. If you're competing against other installers or system designers who are not as analytical, or who are not putting all these factors into consideration, there might be already some very interesting points where you can beat their bids at a very early stage technically. So in this example, as already we've seen for this 408 kilowatt installation, there is a clear 62% clear benefit when you're using the Fronius Echo inverter as far as BOS is concerned, compared to the 60 kilowatt competitor inverter. Let's now look at the Opex analysis. And the Opex analysis, of course, these are the ongoing daily expenses for commercial operations. And the Opex consists of both planned and the unplanned service calls. So major planned service activities for commercial systems would include the following. This would be module cleaning. We have also cable connection inspection, so that after every so often, you need to be sure that the cables are still holding on, maybe in the DC combiner areas or AC areas, to make sure that there are no loose connections. Then cleaning of the inverter cooling system, and that also has a huge impact on also the total system yield, as you're going to see later. And then, of course, checking the parameters on the PV side as far as voltage and current is concerned. Are they correlating to what was initially installed? So, and so forth. So if you look at what the advantage the Fronius inverter is going to give you as far as the Opex analysis is concerned. So we are going to compare an actively cooled Fronius Echo inverter and a passively cooled competitor. So a passively cooled inverter in this case would require more cleaning. This prevents therefore yield from dust accumulation on the cooling fans. Because it doesn't have active cooling technology, it means that there's possibility for dust to hold on to the cooling fins, and therefore dissipation of heat does not happen as efficiently as when you have an actively cooled inverter. So of course, we also look at the service concept of the Fronius inverter, as already mentioned by my colleague Cyprian. If you look even at the Tauro inverter, there is a concept of replacement of parts instead of replacing the whole inverter. And therefore, with the board replacement concept, this allows only very few people, if needed, to go to site for every service call. And then for larger commercial inverters, we require at least 2 people. If you have to bring down the entire inverter without the service concept of PC board replacement. And this might also require, if the system is roof mounted, crane arrangements to be made to bring the inverter from the roof, and as well as to put a new inverter back to the roof. So therefore, this means therefore simply that the more manpower you have, the higher costs that you're going to be looking at as far as Opex is concerned. So tabulating these results, we can see that for every service call that you're going to make per year, we have a passively cooled device, and the scheduled maintenance, you're going to be there for about 2 times per year. Service call outs, probably about 1 per year. And then in terms of how many people you require, we can see 1 person in each case, even for the Fronius Echo. And then the duration of time, we can see, but the most interesting bit would be once you bring all these costs together, including what are the hourly labor costs, and the hourly labor costs would also include things like the transportation to sites and things like that. But you can also sort of put these figures to fit your local conditions. So we don't have to rely on an analysis that was done for a system elsewhere. So you can use this particular example to say, this is my projected OPEX for this particular installation. And therefore, we can see that using a Fronius Eco inverter, you have a clear advantage. So the Eco inverter is giving you savings of approximately 1,000 euros per year as far as OPEX is concerned in this case. Then in terms of energy yield, of course, becomes a very important topic. As we have already mentioned, talking about an actively cooled inverter or a passively cooled inverter, what is your choice as an installer or a system designer? You want to ensure that your customers are going to get the highest yields over the lifespan of the system. We have seen from the initial presentation by my colleague Mohammed that an actively cooled device will start derating at a later stage as far as AC output is concerned. And therefore, the later derating compared to the early derating of a passively cooled inverter would mean that an actively cooled inverter is going to give you more yield over the life of the system. However, looking at also Capex and also OPEX comparison, these only are not enough to determine how cost effective that system is. The expected energy yield should strongly inform, therefore, what is your inverter choice. So the expected over the actual energy yield when you designed your system determines your return on investment as well as the levelized cost of energy. And then to express the levelized cost of energy, you just add your OPEX plus CAPEX, and then you divide what is your energy yield per kilowatt hour over a given period of time. And therefore, this gives you the yield in euros per kilo or unit currency per kilowatt hour. So looking at these two examples that we have considered before, an actively cooled Fronius Eco 27 and a passively cooled 33 kilowatt competitor, what therefore would be the effect on the yield due to derating behavior as already mentioned. So we are talking about a PV system simulation that we had earlier looked at of 408 kilowatt peak. Specific energy yields for the two inverters are shown below. So we can see that the Fronius Eco is giving you an advantage looking at the energy yield analysis of about plus 4.17% in yield increase. And therefore, actual earnings and savings based on this data, how would therefore the situation look over a 15-year period or over the life of the system? So if you go over the life of the system, we are going to see that the Fronius system or the Fronius inverter is going to give you an earning advantage of about 41,000 euros over the entire lifespan of the inverter. And therefore, this becomes a very important point of your discussion with customers or yourself as a designer when trying to understand which specific inverter type should you go for. And therefore, we highly recommend from our case, from our side, that you go always for an actively cooled inverter to guarantee highest possible production over the expected lifespan of the system. So, and therefore, we've come to the end of our presentation today with that information. But before we end, I would like to give you further information on where you can get more details regarding our products and solutions. So from our website, there are a lot of resources there. Also, we have a dedicated YouTube playlist for the Africa region, Sub-Sahara region. So you can get this link once we share the webinar with you. You can go there directly and watch all our recordings for past webinars at your own time. And then in terms of further information, if you have any queries regarding this particular webinar or you have other technical or sales questions that you'd like clarified, as already mentioned, depending on your region, please do get in touch with any of us and we'll be more than happy to give you all the information that you may require. And with that, we would have come to the end of our webinar for today. And I would like to thank my colleagues, Mohammed and Cyprian, for their presentation. And also all our attendees today for taking your time to be with us. And we hope you enjoyed our webinar today. And we look forward to hosting you for the next planned webinars as we go along. So we will also remain online for